Hello, my name's Aaron Badwan, and today, alongside Isaiah Donoso, Kareem Vilbron, and Trevin Kim, we will be presenting our orbital mechanics final project, trajectory from Earth to Jupiter. Beginning with our outline of our presentation, we'll begin with the introduction, providing a bit of background on the moon Europa and the significance of our science mission. Second, we'll begin with our mission overview. We'll provide a summary of our mission goals, concepts, and primary results. Next, we'll go to our modeling and assumptions. We'll provide the key assumptions used in the design process of our trajectory while explaining theoretical frameworks and different constants. After that, we'll move on to our technical calculations and analysis. We'll provide a detailed breakdown of our trajectory design and optimization. We'll provide analysis of our flyby geometry and other critical mission parameters. And we'll end with our mission summary. Our introduction. So this mission focuses on designing an efficient interplanetary transfer from the Earth to Jupiter with the primary objective of observing the Jupiter's moon Europa. Our chosen trajectory has the following parameters. Our launch date has been chosen January 6, 2029 from Earth at Kennedy Space Center. Our time of flight to Mars is 107 days. Our flyby date from Mars will be April 23rd, 2029, with time of flight to Jupiter being 1,326 days. Our arrival date will be December 9th, 2032, and our total time of flight will be 1,433 days. Our wet mass will be 5,200 kilograms, with wet mass needed being 5,198.33 kilograms. This trajectory will use a Falcon Heavy expendable rocket and allows for a dry mass of 2,000 kilograms to achieve our desired hyperbolic escape velocity. Next, we'll provide a bit of our mission overview. So our mission, of course, focuses on designing this ballistic trajectory to Europa. The primary mission goals will be to deliver the spacecraft from Earth to Jupiter's capture orbit with the potential to encounter Europa every 198.4 days. The significance of this will be to investigate Europa's potential habitability by studying and analyzing its subsurface oceans, surface geology, and composition. A few of the key design parameters used for this trajectory. Our launch vehicle, of course, is the Falcon Heavy expendable. Our launch window is between January 2026 and December 2030. And our trajectory constraints in designing this trajectory, the first was a maximum transfer time of 4 years and at least one flyby past Mars for a gravity assist. And next, I'll pass it over to Trevin.
Thanks, Aaron. All right. Yeah, so to kind of go over our mission overview, some of our concepts that we were trying to go over was to be able to develop a trajectory plan by including flyby geometry and, going over a optimal orbital parameters as well, generating port shot plots to show feasible launch windows, and creating a mass budget to be in compliance with our matrix to verify adherence to the mission requirements as well. Some critical results that we came out with a successful Jupiter orbit insertion. The mission delivered the spacecraft into Jupiter's capture orbit within the 4-year transfer time. This achievement demonstrated effective trajectory design, being able to use the gravity assist, efficiently using energy management with our allotted wet mass included. Mars gravity assist, the Mars flyby also provided the delta V boost needed to be able to reduce propellant needs while going with the adhered maximum transfer time, being able to do the flyby trajectory aligning with the destination launch constraints as well, while also creating a low energy transfer. We'll keep moving along. So kind of going into our modeling and assumptions of the mission, just kind of our overviewing, right? Our mission involved traveling from Earth to Jupiter to study Europa. The spacecraft would be using a ballistic transfer trajectory towards Mars for a flyby, using a gravity assist, and then ending at Jupiter into its capture orbit, to be able to periodically encounter and intercept Europa in its wake. Kind of going over some assumptions for the calculations for the overall trajectory. The orbit was obviously from Earth to Mars and to Jupiter, assuming the circular and coplanar orbits as well, ignoring any perturbations from any other celestial bodies, right? So the sun was our body, our center body. Um, there were gravitational parameters as well, needing to go ahead and correct for the sun, Earth, and Mars, with Jupiter alone being the gravitational constants in those windows. Being able to launch and arrive within our optimal windows with our trajectory, and using our engine efficiency, high engine for our 450-second impulse as well. We can go and keep going along. And some of those trajectory gravitational parameters also came with, the sun, Earth, Mars, and Jupiter as well. The sun being at 1.327 times 10 to the 11th, and then Earth being 3.98 times to the 5th, Mars being 4.283 times 10 to the 4th, and Jupiter being 1.266 times 10 to the 8th as well, with obviously a larger radii for Earth, smaller for Mars, and the largest with Jupiter as well. So some key equations and definitions that we did go over were to be able to calculate for the orbital period, the time needed to be able to complete the one orbit around the sun using Kepler's third law, the transfer time to be able to calculate the time along the trajectory for the transfer orbit, being half of the elliptical transfer orbit as well, with no return, right? Phase angles, being able to calculate for the phase encountered based on the orbital positions of Mars and Earth and Jupiter to Earth as well. The delta V, the velocity changes between each of the maneuvers, including the flyby with Mars and the hyperbolic trajectory used along the way. So some of those tools to be able to calculate those were MATLAB, and NASA's JPL Horizon system to give us the planetary positions.
Okay, so here we have some of the major formulas that were used along with the flowchart that was provided to generate the computer program. We did all of our coding in MATLAB, and all of the pork chop plots were also developed in MATLAB. Those are provided below in the appendix. The Lambert solver that we used was also provided in the code below. If we could get the next slide. Okay, yeah. So here we can see the pork chop plots that we use to find our available mass for the C3s that were calculated. The upper left pork chop plots show from Earth to Mars, and the bottom right show from Mars to Jupiter. And then here we have a graphic of the total trajectory from Earth to Jupiter with the flyby from Mars. And it shows the arrival date and the V infinity at arrival. Yeah, unfortunately, we weren't able to develop a backup trajectory plan in case of any mishaps. We were only able to find the one.
So, in summary, the mission involves the design and analysis of a ballistic interplanetary transfer trajectory from Earth to Jupiter, with a focus on reaching and studying Europa, one of Jupiter's moons. The trajectory design incorporates a Mars flyby, as mentioned before, for gravitational assist, and optimizing the transfer time and minimizing the total velocity change that we have. The following key points summarize the mission analysis. The trajectory design was a transverse trajectory was utilized for the Earth to Mars segment, and also from the Mars to Jupiter transfer. The Mars flyby is strategically incorporated to leverage gravitational assist, reducing fuel consumption, as we only had a limited amount of C3 for the expendable Falcon Heavy rocket, So we are unable to just do it all by consuming fuel, so the gravitational assist was used. The orbital parameters, as you can see, or the semi-major axes and eccentricity of the transfer orbit, they were calculated with the perihelion and aphelion matching Earth and Mars distance from the Sun. We used the orbiting radii for that, and the total transfer time, including the Mars flyby, ensures alignment with Jupiter at arrival. We tried to keep the date that the rocket arrives to Mars and it departing from Mars to Jupiter quite close, so it doesn't have to orbit Mars. It can just do a flyby to minimize the time of flight it takes to get to Jupiter. And some of the key performance metrics is that the total velocity changes required for departure from Earth, the Mars flyby, and arrival at Jupiter were calculated to assess propellant needs. Again, as we mentioned before, we had a limited C3 to work with. It was 80 kilometers squared per second squared, I believe, for a 2,000 kilogram dry mass, according to the NASA website that shows the vehicle launch performances. Second thing is that the gravitational assist at Mars significantly reduced the energy required for the second leg of the mission. And the computational approach that we took was, again, MATLAB. It was employed to perform almost all of the calculations. The only thing that we got out of elsewhere, I believe, was the NASA website in order to get the C3 versus mass graph, and that will be shown also in the appendix. And the pork chop plots were also generated in the MATLAB in order to get the time of flight, the C3, and the launch date that we actually needed. Assumptions and constraints were that planetary orbits were assumed circular and coplanar for simplicity, and perturbative effects neglected. Specific impulse values were chosen to represent high efficiency propulsion systems commonly used in deep space missions. And in the next slide, we'll be able to look at all the requirements. And as we can see, the launch did take place from Kennedy Space Center, as the initial launch date was January 6th, 2029. So it falls in between the window that we were given for launch. The spacecraft shall be launched on a Falcon Heavy expendable, which is correct, and that is why we optimized our trajectory in order to be able to account for the limited C3 that comes with the expendable heavy, the Falcon Heavy expendable, I apologize. And the total transport time between Jupiter and Earth shall not exceed 4 years, and that is also true. As you can see, that our total time of flight was 1,433 days, which is less than the 4 year allowed time frame. And the spacecraft shall be equipped with a 450 ISP engine and shall have a dry mass of 2,000 kilograms. Again, we use the NASA Launch Services Program in order to get the performance of the Falcon Heavy, and we kept the trajectory uh, the way it is in order to obtain the best C3 to allow for a Falcon Heavy. The trajectory should include at least one planetary flyby at Mars, which is correct. We did do a flyby at Mars 107 days from launch. The unfortunate part is that we were unable to do more flybys, even though it would have saved more fuel. However, it would have taken longer. And that is why we're unable to do that. And the initial capture orbit around Jupiter shall allow potential encounters with Europa every 198.4 days, which is true. The actually capture orbit was designed in order to be in order to allow an encounter with Europa with every 198.4 days. And again, you will be able to see that in the MATLAB code provided below. And as for the extra credit, the Apple Apps for the Apple Apps to be lowered, unfortunately, we're unable to do that as again uh, our mass budget was 5,200 kilograms, but we needed to use 5,198.33 kilograms of that in order to reach Jupiter. So we were only left with 1.34 kilograms. So unfortunately, we were unable to do that calculations. In the next slide, you'll see that, and the MATLAB code and the rest of the resources that were provided by Professor Maggio will also be uploaded to Canvas in order for you to be able to view it. Thank you.